So now we're going to look in more detail at what is going on in between molecules as they form a solution. And so what is that impact of intermolecular forces on something's solubility? I want to start with a kind of straightforward example and look at two simple sets of intermolecular forces for our solute and solvent. So I've got octane here, which is, C8. H18, and I have tetrachloromethane, so CCl4. These are both nonpolar compounds, and the octane is a larger molecule, like it has more surface area than my tetrachloromethane. Those chlorine atoms are pretty big though. So they are not perfectly the same in any way, and they'll have slightly different London dispersion forces. So what I would do to consider will these combine or not is I would compare the intermolecular forces of just the solute particles, just the solvent particles, and then how they would interact together. So within my solute-solute interactions, these are just going to be London dispersion forces. I'm going to abbreviate that LDF. Now, my tetrachloromethane also only has London dispersion forces. I would go out on a limb and say that I think that the octane is going to have stronger London dispersion forces than the tetrachloromethane because it has more surface area. At the same time, these aren't going to be too terribly different because the tetrachloromethane molecule is pretty big still. Now, when they come together and interact, instead of thinking about what are the intermolecular forces that exist just within a pure sample of each of these compounds, I'm going to ask the question of what happens when they interact with each other. So imagining what happens to and I'm just going to kind of highlight this here, a octane molecule when it's completely surrounded by tetrachloromethane. What intermolecular forces exist between those two molecules? And now they're both nonpolar and they don't have any hydrogen bond capability, and neither of them are an ion. So the only thing that will happen in between them is London dispersion forces. So when I'm breaking apart my solvent-solvent interactions, my solute-solvent interactions, I kind of envision this as I have these pure samples and I create space between all of my molecules in the liquid. And then I'm going to combine those two together and form new interactions. And so what's happening in this top part, or this left side right here, is that we break the intermolecular forces that exist between each of the molecules. And that's going to be a process that requires energy. To break the attraction between two particles, we have to input energy into that interaction to break it. So this is going to be an endothermic process. It means it's going to absorb energy. Now, when I think about my solute-solvent particles and coming together, I've separated out. So I have my solute and my solvent and solvent particles interacting. I separated them. That took a lot of energy. Now I'm going to bring them together and I'll bring them close together and they'll be able to interact. And so I'll be able to form intermolecular forces or forces of attraction between those particles, which will release energy. Right? So these are favorable interactions that stabilize them and it releases energy when that occurs, which makes it an exothermic process. So when we bring these together here, it's exothermic. Now, if that's a net, like if the amount of energy that goes into separating things is the same amount of energy I get from bringing them together, then this is going to form a solution. Even if it's not perfect, even if it's just a little off, it'll probably still form a solution because it will have that tendency to form a solution, to mix. That tendency to mix will be a driving force that allows me, or that allows these molecules to combine and get some sort of net energy benefit that can overcome slight deficiencies in regaining that or releasing the energy that was used to break intermolecular forces. And so this brings us to this super handy little rule that we have, uh, that is like dissolves like. And in its simplest form, we usually use this to mean things that are polar tend to dissolve polar compounds, and things that are nonpolar will dissolve nonpolar compounds. But we can take it in a little bit more granular level, and we'll say things that have similar intermolecular forces will combine and form a solution with other molecules that have similar intermolecular forces, because the amount of energy it takes to break apart intermolecular forces is the same energy that is gained, released, when you bring them back together. So if I'm separating them and then reforming interactions with something very similar, I'll have this like net change of nothing. So when we look at it, we looked at just London dispersion forces and London dispersion forces in my solute and solvent, and then combining those to have the same London dispersion forces. So this would be soluble. We have similar intermolecular forces that form similar intermolecular forces. And the ones that we're going to be looking at here are dispersion forces, dipole-dipole forces, hydrogen bonding, and ion dipole interactions. And so if our solute has a similar list of intermolecular forces as our solute solvent interactions, and our solute IMFs have similar IMFs as our solute solvent, then it's going to form a solution. So this means that we need our solute and our solvent to have similar, not exactly the same, but similar structural features. Like if something is polar, it will be more likely to dissolve in a polar solvent. If it has lots of hydrogen bonding capacity, it's more likely to dissolve in something that has hydrogen bonds too. Ionic compounds are more likely to dissolve in polar solvents and very unlikely to dissolve in something that's nonpolar. And we see our nonpolar solvents or compounds dissolve in nonpolar solvents. This really gets us to things like water and fat soluble vitamins, right? Some vitamins that our body needs are going to be nonpolar or predominantly nonpolar and are more likely to dissolve in fats. Whereas some of the vitamins that we need have a lot more polarity and hydrogen bonding capability, and they're going to be more likely to dissolve in water. Let's look at an example of this together. So I know water is the universal solvent, but from a chemist's perspective, it is definitely not the universal solvent. It's great at dissolving polar compounds because it is very polar, and it forms a lot of hydrogen bonds. But like the universal solvent would be something that could dissolve a lot of polar compounds and a lot of nonpolar compounds. Saying. So one that I like, there's a couple of these. So just straight up nail polish remover is acetone. And acetone is a fantastic solvent for just about everything. It's also low molecular weight. It just evaporates away. So I always say, like, if you're struggling to clean something, throw nail polish remover on it. But like, don't take my advice on things that are safe at all for humans. So another one is THF. This is one of my favorite ones. And so I have it written here, and let me draw it out for you because C4H8O can be a lot of things. And so what I'm intending when I say CF or C4H8O is this one right here. It's a 5-membered ring of carbons and 1 oxygen. Got some lone pairs. And there's hydrogens bonded to each carbon. So what we're going to do is we are going to compare how this would dissolve something like acetonitrile and something like water, and compare intermolecular forces and decide if we think that it would dissolve them. And we could kind of loop back and actually look at solubility. So in this THF molecule, I'm going to have interactions that are going to include London dispersion forces because I have electrons. So I've got London dispersion forces. And we're also going to have a dipole moment, a slight one. It's not huge, right here at the oxygen, because these carbon oxygen bonds are both polar bonds, and they're not 180 degrees apart because of the 2 lone pairs in the oxygen. So it creates a slight dipole moment. This is an ether, and ethers don't have strong dipole moments, but they're there. So it'll have London dispersion forces and dipole-dipole interactions. Now let's consider our other two molecules. And when I'm doing a comparison like this, I like to just look at one and list its intermolecular forces as it would be for a pure compound before starting to think about how things mix. So Ch3cn Acetonitrile, this is another really common solvent in chemistry labs, just like THF. So this will be carbon bonded to 3 hydrogens, bonded to another carbon, triple bonded to a nitrogen with a lone pair. Now, this is another one that is polar. It's not a huge dipole moment. It's just along this carbon nitrogen bond right here. So we'll see London dispersion forces, and we'll see dipole-dipole interactions. Now, neither of these actually have the ability to hydrogen bond, because in neither of these molecules are there an oxygen hydrogen, nitrogen hydrogen, or fluorine hydrogen bond. All right, let's look at water last. So I'm going to draw this out. Hopefully this one is super familiar by now. So this water molecule has a dipole moment. It's a stronger dipole moment than our ether because the electronegativity difference between the oxygen and hydrogen is greater than the oxygen-carbon electronegativity difference. And so it just creates a larger dipole moment with a larger magnitude. So we'll have London dispersion forces because we have electrons, dipole-dipole forces, and we have these oxygen-hydrogen bonds right here that are going to be hydrogen bonding interactions. So now that we have all of our intermolecular forces for each of these, we can kind of evaluate what IMFs form when we combine two of the compounds. So let's start with A. When we combine our THF and our acetonitrile, they're going to come together and they'll both have electron clouds. So they'll both have London dispersion forces. They'll both have dipole moments, so they'll be able to create dipole-dipole interactions with each other, where the partial positive end on an acetonitrile will line up with the partial negative end of a THF molecule. It still won't be able to create hydrogen bonds between these because there aren't any OH, NH, FH bonds. So we'll just have these two right here for this combination. So looking at that, if we just are focusing our attention on these two right here, we can see that we're going to have to put energy into breaking our THF London dispersion and dipole-dipole interactions. And we'll have to put energy into breaking our London dispersion and dipole-dipole interactions on our acetonitrile. But when we form them, we're going to form London dispersion and dipole-dipole interactions again between all of our molecules. And so the energy we're going to put into breaking intermolecular forces will be released again as we form them. And we'll be forming the same interactions. They're relatively the same size molecules, so we can assume that while their London dispersion forces aren't exactly the same at all, they won't be too different. So we can say that this will definitely be a soluble mixture, that our THF as a solute will easily dissolve in our acetonitrile as a solvent. In fact, later on when we talk about ideal solutions, this might be an example of something that's close to ideal. All right, now let's focus on water and THF and their combination. So when we combine these together, we are going to be able to form London dispersion forces. Everything's got electrons. They both have dipole-dipole moments, so we're going to be able to form dipole-dipole interactions as well. Now, hydrogen bonds. So we can form hydrogen bonds between our water molecule and our THF molecule. So what happens is these lone pairs on our, let me switch colors, on our THF right here can form a hydrogen bond with a water molecule. Yeah. Now, it can't form a hydrogen bond to the water molecule with a hydrogen. Like, it doesn't have that ability, but it can participate in the hydrogen bonding. However, this THF molecule can only participate in 2 hydrogen bonds with its lone pairs. And so it it's going to be able to do some of this, but it's not going to be like another water molecule hydrogen bonding. And while it's going to interact with this lone pair, it won't be as strong of an interaction as it would with another hydrogen bonding capable molecule, because this oxygen right here has less electron density or less partial negative charge. Let's say that less partial negative charge than this oxygen on the water. And so it's not as strong of an interaction as the hydrogen bonding that's going to take place between the water. So we'll see some, but it's going to be weaker than what we had before. So we can say that it has hydrogen bonding interactions, but they're weaker than the water ones. So looking at this, we can say, all right, we're going to put some energy into breaking up our THF and some energy into breaking up our water molecules, intermolecular forces. And when we bring them together, our hydrogen bond, or sorry, our THF molecule is going to experience stronger intermolecular forces than it did in its pure substance. And our water is going to experience slightly weaker intermolecular forces than it did in its weak substance. And so I would predict that this forms a solution, especially with that driving force, that tendency to mix that will release some energy as we bring these together and distribute their kinetic energy throughout the system. It's very likely we'll form a solution. So how do you double check all of this? So what we'll do is we'll look up the solubility of these really quick. Like we can go, remember we talked about how solubility is this physical property that we can learn about. So let's go ahead and do that. And when I look this up in a CRC handbook, it says miscible. So it doesn't give me a measurement of like X grams or anything like that. But it does say that our THF and our water will be able to form a homogeneous solution and that they're soluble in one another. So